Hello, students. How are you all? I hope you all are doing good. So, my name is Aditya Jain from askIITians, and today we are here to discuss the chapter of a grade 10, which is magnetic effects of current. Okay, the name of the chapter is magnetic effects of current. So, if I talk about the last chapter, in the last chapter we have already seen one effect of current, that is heating effect of current. Okay, that one effect we have already seen in the last chapter. In this chapter, we are observing magnetic effect of current. So the foundation of this concept, which I am naming as magnetic effect of current, was laid by a scientist, which is known as Oersted, Henry Oersted. So Henry Oersted performed some experiments, and from the conclusion of that experiment, or from the observations of that experiment, he concluded the magnetic effect of current. So what is actually magnetic effect of current? That whenever any current flows through a conducting wire, whenever any current flows through a conducting wire, it will produce a magnetic field. So what is happening? Due to the flow of current through a circuit, a magnetic field is produced. A magnetic field is produced that is known as the magnetic effect of current. In this chapter, we are going to discuss Oersted experiment, and the complete chapter is revolving around this Oersted experiment only. That whatever the conclusions he is generating from the Oersted experiment, the whole chapter will revolve around this. Okay, so see what we are going to today learn are these topics. First, we are going to see what is actually magnetism. Then we will see magnetic field lines, then field due to a current carrying conductor, and then magnetic field due to current carrying coil or solenoid. So this much topics we are going to discuss in today's class. So ready guys? Yes, ready students? Okay. So let's start with the Oersted experiment. Said what does Oersted did? Oersted's experiment. So what he did, he took a circuit, he took an electric circuit connected with some variable resistance, a key, and a cell or a battery. Okay, and on this conductor, he connected one end with a copper wire. Suppose this is a copper wire, the thick wire I am making. Suppose this is a copper wire. So what he observed, he placed a compass needle. He placed a compass needle. And you know what is compass needle used for? It is used for finding the direction of magnetic field or to detect whether a magnetic field is present or not. Yes or no? So what was observed? As he switched on the circuit or as he closed the circuit, the current started flowing in the circuit and the same current was flowing through this copper wire. So what he observed that when the current starts flowing through the circuit, there was some deflection. There was some change in deflection observed in the compass needle. There was some deflection or change in deflection observed in the compass needle. So what he concluded that due to the presence of current or as the current starts flowing, there was some deflection in the compass needle. But as he switch off the circuit or the circuit is now open, the current suddenly stops. So as the current stops flowing, the deflection was again come back to zero or to the normal position. So what was the conclusion? That when the current was present, there was some deflection in the compass needle. When there was no current present or no current flowing in the circuit, there was no deflection in the compass needle. So that was the first conclusion. What he did next, he just increases the value of current by changing the battery. So he changed the battery, increased the value of current. So he increased the value of current. So what he observed that the deflection was more. This was the second conclusion. The first conclusion was that whenever current is flowing, it produces a magnetic field around it. Because the deflection was shown by the compass needle, it produces a magnetic field around it. This is known as magnetic effect of current. That whenever a current is flowing in a circuit, it produces a magnetic field around it. That property of current or the effect of current is known as magnetic effect of current. So this effect was given by Henry Oersted by this experiment, magnetic effect of current. Okay. Here now the second conclusion is that when he increases the value of current in the circuit by increasing the voltage of the battery, then what he saw, the deflection in the needle was more. So we can conclude that the magnetic field will be more. Because if the deflection is more, that is due to the magnetic field. So if deflection is more, we can conclude the magnetic field is more. So current was proportional to magnetic field. Magnetic field is shown by a symbol B. So this is the second conclusion. Then when you increase the value of current, the magnetic field increases, which is shown as the more deflection in the compass needle. The third thing which he did was that he take the compass needle away from the circuit. He took the compass needle away from the circuit. So as he was trying to take the compass needle away and away from the circuit, the deflection was getting decreased. The deflection was getting decreased. So can I say for the same value of current, for a constant value of current in a circuit, if the distance of the compass needle was increased from the circuit, then the deflection becomes less. So you can conclude that the magnetic field is now less at a larger distance. So what he concluded that with the increase in distance from the circuit, the magnetic field decreases. These were the three main conclusions drawn from the Oersted experiments, that whenever a current is flowing through a circuit, it will produce a magnetic field around it. The second was that increase in the value of current. When you increase the value of current in the circuit, then what will happen? The magnetic field will increase, which is shown by increase in deflection of the compass needle. But yeah, when you were increasing the distance from the circuit, the magnetic field was decreasing. The magnetic field was decreasing, which was shown by the less deflection in compass needle. The deflection in the compass needle was less in comparison to the previous case. So these are the three main conclusions of the Oersted experiments, which marks the beginning of this topic, magnetic effect of current. Clear? Now see next, magnetism. So what we are going to interested, I was constantly using the word magnetic field. I was using the word magnetic field. So in our childhood days, all have played with magnets. Yeah, we have all played with magnets. So suppose this is a magnet, this is another magnet. So what we do, we used to take them near to each other, and they will kind of attract each other. So that is the force acting on them. Which is known as magnetic force. So magnetism field, if I ask you what is magnetic field, it is basically an invisible region around a magnet. Magnet is the material which shows magnetic properties. Magnet is that material which shows the properties of magnetism. What is magnetism? Magnetism is just like that. If you bring a magnet or a metal near to a magnet, it will either attract it or repel it. That property of attraction or repulsion is something known as magnetism. So magnetism is the property possessed by a magnet. Magnet is that material which has the property magnetism. And magnetic field is the region or invisible region around a magnet. Suppose this is a magnet, so this is the region around a magnet in which if you bring any other magnet, suppose I am bringing any other magnet or I am bringing any iron material, so that will experience either attraction or repulsion. So that invisible field around a magnet is known as magnetic field. Okay. And you know, as the properties of charges is there is a property in magnetic poles also. A magnet consists of two poles. A simple example of magnet is a bar magnet. So bar magnet is a rod-like structure like this, which is having two poles, North Pole and South Pole. So basically there are two poles in a magnet. One is North Pole, other one is South Pole. Okay. And there is a property also that North Pole and North Pole, or South Pole, or you can say like poles. Like poles means if north is facing north or south is facing south. So like poles will repel each other. Or like poles will repel each other. And what about unlike poles? Unlike poles means north and south are facing each other. So unlike poles will attract each other. Clear? So basically magnet is a material which shows the property of magnetism. And there is a region around a magnet in which any magnetic material is placed, then that will experience either attraction or repulsion force. That is known as magnetic field around a magnet. And a magnet consists of two poles, North Pole as well as South Pole. Like poles, that means either north-north or south-south. They will repel each other, and unlike poles mean north or south. They will attract each other. So that is the thing. Clear? So this is magnetism. Magnetism is the force exerted by the magnets when they attract or repel each other. So this is basically a property. This is the property of a magnet by which it is either attracting or repelling any other object or other magnet. So you can see in this diagram also, this is a magnet which is in the shape of a horseshoe. That's why it is known as horseshoe magnet. This is known as horseshoe magnet. So you can see this magnet is attracting these iron balls. Yes, due to the property which is known as magnetism. In the same way, this second horseshoe magnet is attracting these iron nails. This second horseshoe magnet is attracting the iron nails by the same property which is known as magnetism. So I think magnetism is clear. What is the magnetism? And now the second thing is magnetic field lines. Second thing is magnetic field lines. So what are magnetic field lines? Suppose if I give you a picture like this. What I have done here, I have taken a bar magnet. And I have placed numerous number of iron nails. I have placed, or I can say I have just dropped. I have just dropped numerous number of iron nails near the bar magnet. So the iron nails will automatically align themselves in this shape. So this is the shape you will observe when you split or when you spread iron nails around a bar magnet. This is the shape you will observe of iron nails. So what you can see, if I make this picture as a solid picture, then I will see like this. These are the lines which are looking like curved lines, you can see. These are actually looking like curved lines. And if you can see at the ends, it is looking like this. It is looking like this. And at the end, south pole, it is looking like this. So basically what has happened when you have spread or when you have taken iron nails near to a bar magnet, then that iron nails are aligning themselves in a particular line or in a particular shape. So these lines in which iron nails will align themselves are known as magnetic field lines. Magnetic field lines. So who is causing these iron nails to get a shape like this? Obviously the magnetic field. The force of the magnetic field is causing these iron nails to align in that orientation. So these picture what I have drawn, these are magnetic field lines. So magnetic field lines are what? Magnetic field lines are just showing the direction of magnetic field. Because it is the magnetic field who is making these iron nails to align in that particular orientation. So these iron nails, whatever orientation they are making, that is actually representing the magnetic field direction. And the direction of magnetic field is pictorially represented by something known as magnetic field lines. So magnetic field lines are nothing but the pictorial representation of magnetic field. Magnetic field lines are nothing but the pictorial representation of magnetic field. Because in reality, you cannot observe magnetic field by your eyes, or you cannot see magnetic field by your eyes. So to make that happen on paper, or to draw the magnetic field on paper, we use a concept which is magnetic field lines. Now clear? So magnetic field lines is the region around a magnetic material. Yeah. This is actually the definition of magnetic field. Magnetic field is region around a magnetic material on a moving electric charge within which the force of magnetism acts. So we have seen that magnetic field. What are magnetic field lines? These are pictorial representation. Pictorial representation of magnetic field. So pictorial representation of magnetic field is known as magnetic field line. Is known as magnetic field line. Clear? Magnetic field lines are nothing but the pictorial representation of magnetic field. So now there are some important properties related to magnetic field lines. There are some important properties related to magnetic field lines which we are going to see here. As you can see in this diagram, the first property is that if you can observe there is north pole in a bar magnet, there is a south pole in a bar magnet. So you can see these are the field lines. If you see the field lines are starting, the arrows are showing the direction of magnetic field lines or the magnetic field. So you can see the magnetic field lines are starting from the north pole. They are going like a curvilinear path towards the south pole or ending at the south pole. Yes or no? You can see this arrow also. This arrow means the magnetic field is ending at the south pole. So the first property is that magnetic field lines starts from north. Lines starts from north and terminates at south pole. So this is the first property of magnetic field lines, that magnetic field lines starts from north pole and terminates at the south pole. Now if you see carefully, the second property is that the magnetic field lines form closed loops. magnetic field lines form closed loops, means closed path. Closed loops. That means they are starting from north and going towards the south. That means they are starting from north. Suppose this is north, this is south. So they are starting from north and going towards the south like this. They're starting from north, going towards the south. And if they are forming closed loops, so they should complete their path in the magnet also. Yes, if they are forming closed loop, then they should be forming closed path. So inside the magnet, what you will observe, if the orientation is like this, so to complete the path, the magnetic field line should move like this inside the magnet. Yes or no? To complete the closed loop, the magnetic field line should have to move in this direction. So inside the magnet, direction is from south to north. So inside magnet, direction is from south to north. So we have studied three properties, that magnetic field lines start from north pole, terminates at south pole. Magnetic field lines form closed loops. And third is that inside the magnet, the direction of magnetic field line is from south to north. Direction of magnetic field lines is from south to north. This is the direction, south to north. Clear? Now see next point. What is the direction of magnetic field at any point? So what you see, these are curved lines. So in these curved lines, suppose I want to measure this direction of magnetic field at point P. So you have to draw a tangent here. You have to draw a tangent to this curved path like this. So the tangent will show the direction of magnetic field at that point. The tangent will show the direction of magnetic field at that point. So you can write the property that tangent at any point on the magnetic field lines, will represent the direction of magnetic field at that point. Will represent the direction of magnetic field at that point. Clear? Yes or no? Will represent the direction of magnetic field at that point. So this is the fourth property. This means the magnetic field has different property at different directions, which will be given by the direction of tangent drawn at that point, whichever you are concerned with. Now the fifth property is that two magnetic field lines never intersect each other. Suppose these are two magnetic field lines. So if they intersect at each other, there should be two directions of magnetic field. How I am saying there should be two directions of magnetic field? Let's see. First draw a tangent to this path. So the tangent will be like this. Now to this second magnetic field lines, the tangent will be like this. And you know the tangent is showing the direction of magnetic field. So at a single point, there are two directions of magnetic field coming, which is not practically possible. Which is not practically possible that at a particular point, there are two directions of magnetic field. That's why the property goes as magnetic field lines or two magnetic field lines never intersect each other. Two magnetic field lines never intersect each other. Never intersect each other. Yes, this is clear. Now the next property is there. Suppose I am giving you two situations. Suppose these are the magnetic field lines like this. Okay. So one is point A, one is point B. So you can see the field lines are more closer at point A in comparison to B. Yes or no? The field lines are more closer at point A in comparison to point B. So there is another property which is known as closer the number of field lines or closer the magnetic field lines, stronger will be magnetic field at that point. Closer the magnetic field lines, stronger will be magnetic field. Stronger will be magnetic field. Okay, clear? So if I give you an example like this, suppose I'm just taking an imaginary position. This is point A, this point B. So magnetic field at A will be greater than magnetic field at B because the field lines are much closer at A in comparison to B. So closer the magnetic field lines, stronger will be the magnetic field. So I think we have covered important properties. We have seen 6 properties. Magnetic field line starts from left, terminates at south. Magnetic field lines will form closed loop. Inside the magnet, the direction is from south to north. Then we have seen tangent drawn at any point on the magnetic field lines will represent the direction of magnetic field at that point. Then we have seen two magnetic field lines never intersect each other. Two magnetic field lines will never intersect each other because if they do, then there will be two directions of magnetic field at a single point, which is not possible. Clear? Then we have seen the sixth, not fifth. This is a sixth property. That closer the number of field lines, stronger will be magnetic field. Closer the number of field lines or closer the magnetic field lines, stronger will be magnetic. So I hope the magnetism, magnetic field and magnetic field lines, everything is clear. Yes or no? Thumbs up, guys. Okay. Now we'll move forward basically. Field due to a current carrying conductor. Yes. So we have seen from the Obstadt experiment that whenever current is flowing through a conductor, it generates a magnetic field. And that magnetic field depends upon two things. Yeah. First was current in the conductor. We have seen when we were increasing the current in the experiment, the magnetic field was increasing. And second is the distance of the point from the conductor. And we have already seen when you were increasing the distance of the point or the compass from the conductor, the magnetic field was decreasing. Clear? So this is about the magnetic field. But yeah, now we are concerned with the direction of magnetic field actually. That the conductor is generating some magnetic field. That is correct. But in which direction? The question arises, in which direction? So the answer of that question is given by a rule which is known as right-hand thumb rule. The answer to that question will be given by a rule which is known as right-hand thumb rule. So right-hand thumb rule will give you the direction of what? Right-hand thumb rule will give you the direction of magnetic field acting on a straight current carrying conductor. Acting on a straight current carrying conductor. So what does this rule say? First see this. What does this rule say? If you point your thumb of your right hand, this is my right hand. If I'm pointing the thumb of my right hand in the direction of current, then the curl of my fingers are representing or are giving the direction of magnetic field due to that current carrying conductor. Clear? I am repeating again. So if I point my thumb of right hand towards the direction of current, then the curl of my fingers of my right hand will give the direction of magnetic field around that conductor, a straight conductor. So if from this curl direction, you can see the magnetic field will be circular. The magnetic field will be somewhat circular. If you can observe, suppose, take this example in this picture, the direction of the current in the conductor is upwards. So you are pointing your thumb in the upward direction, in the direction of current, and you are just give a curl to your fingers. So if, according to me, my fingers are curling in anti-clockwise direction. According to me, if I am the observer, you can try it also, yeah, on your side. Just put your thumb in the upward direction and curl your fingers in the like this. Fingers of your right hand like this. So they will curl in anti-clockwise direction according to you. So this is shown in this diagram. They are curled in anti-clockwise direction. You can see this anti-clockwise direction. Yes. So this is the curl of the fingers, anti-clockwise direction. Okay. So this is the direction of magnetic field given by the right hand thumb rule. And you can see the direction of magnetic field is perpendicular to the wire. If you can see, the direction of magnetic field is actually perpendicular to the wire because the current was like this in this wire upward and the magnetic field is in circular plane. So this is kind of perpendicular. If you can see, the plane of the magnetic field is perpendicular to the wire. Yes or no? This is the wire. This is the magnetic field. So this is perpendicular. This plane of magnetic field is perpendicular to the current. Okay. So this was about the current carrying coil. Straight current carrying conductor. If the current is flowing through a straight current carrying conductor, then the direction of the magnetic field will be given by right hand thumb rule. Clear? And it will be perpendicular to the wire. Done? Okay. Now there is something known as coil also. There is something known as closed coil. Now we are not concerned about straight conductor. Suppose there is a coil which is, the coil itself means it is a circle. Coil itself means it is a closed one. So what you will observe, it is basically made up of different number of, or you can say infinite number of straight conductors. So if I explain you the direction of or field due to current carrying coil, suppose this is the direction of current given. So actually the current is flowing in anti-clockwise direction according to us. We are the observer now. So if you observe the screen, the direction of current is in anti-clockwise direction. So suppose I am taking this point. So for this small particle or for this small element, suppose the length is like this, tangential. For a small particle or for a small length, I can assume the length as tangential. And the direction of current was like that. Direction of current was like that. Yes or no? This was the element. This is the direction of current. So if you take the right hand rule for the straight conductor of small length, very small length, so you will point your thumb towards you. You will point your thumbs towards you. The direction will be like this. Direction will be like this. So this is the direction you are observing here at the corner. See, this is the direction we are getting. And again, if I take at this end a small element, the direction of current through this element will be like this. So if you use the right hand for a very small element of straight conductor like this, then curl of the fingers will be like this. Now you are observing we are getting this direction again. So if I define magnetic field due to current carrying coils, the magnetic field due to current carrying coil are concentric circles. And for everything they are concentric circles, because when we were observing about straight conductor, then they were also concentric circles. Yes, the thing is that the intensity of magnetic field decreases as we move away from the conductor, and the intensity of magnetic field increases as the current in the conductor increases. That we have seen from the Oersted experiment itself. But the thing is that the magnetic field lines are concentric circles. Magnetic field lines are concentric circles. So if you observe in the case of coil, suppose this is a coil, the direction of current carrying conductor was like this. They are concentric circles. So as you move away from the coil towards the center, the radius of this concentric circle starts increasing. Yes or no? Increases. They are getting bigger circles. They are getting bigger circles. So if you observe at the center, the radius of these circles, concentric circles, are so big that they appear to us as a straight line. So you can see in this also, when you are talking about the coil here, if I am observing the center of the coil, that they are looking like a straight line. As you are moving away from the center towards the coil, they are making complete concentric circles. So still the direction can be found by the right hand thumb rule by taking small elements. But the thing is that as you move away from the coil, the lines become straight. Near the center of the coil. So the field due to current carrying coil is given by here. Magnetic field lines are concentric circles at every point of a current carrying circular loop. The direction of magnetic field at every section of the circular loop can be found by using the right hand thumb rule. That's what I was saying. At every section means at every small element, the direction of the magnetic field due to the coil can be found out by right hand thumb rule by considering a straight conductor of very finite length at any point that we have discussed at these two corners. So I think this is clear. Due to current carrying coil, these are concentric circles near the coil. And as you move towards the center, they will be forming a straight line. They will appear as a straight line magnetic field. Clear? Now see how to decide the direction. There is another rule which is known as clockwise rule. Suppose this is a coil. We are observing it from here. So suppose the direction of current is this. And this is the clockwise, this is anti-clockwise. This is the clockwise. And this is anti-clockwise. Okay. So if you see, I am making anti-clockwise direction. So if you observe, there is a rule basically known as clockwise angle rule. What you make clockwise as clockwise will be make like this. So if you join this, they will form N. Which is known as North Pole. And if I make a clockwise, anti-clockwise direction like this, and if I join these, what will I get? Yes. What will I get? Yes. I'll get a N. This is a S. This is a N. This is a S. This is a N. So this is a coding basically. If the coil or the portion of the coil which you are observing, if the current is flowing in clockwise direction, then the side which we are observing is behaving as a south pole. The side which we are observing is behaving as a south pole. And if you are observing the current in the anti-clockwise direction in the coil, then the side from which we are observing will be north pole. So clockwise means south pole and anti-clockwise means north pole. So the direction or the point of the coil away from us or behind this point will be north pole then. And you know what will be the direction of magnetic field? It will be starting from now north and terminating at south. You can see here. If you can see, observe here, this was north, this was the south. So the field lines were emerging from north and going into the south. And inside the coil, they were from south to north if you carefully observe. So the case is same, starting from north, terminating as south. It is a way of perceiving things. That for a circular coil, you will observe like this. Clockwise means south pole is towards us. Anti-clockwise means north pole is towards us. So the behind portion will be south pole and magnetic field lines will be emerging from north to south poles. They are concentric circles near to the coil, and at the center of the coil or near to the center of the coil, they are just straight lines. They are just kind of straight parallel magnetic field lines. I hope clear. Okay, now see, there is something known as solenoid. There is something known as solenoid. So what is actually solenoid? If I simply define solenoid, it is a laminated copper wire. You can say laminated and coiled copper wire. Yes, laminated and coiled copper wire is something known as solenoid. So solenoid is something like this. Solenoid is something like this. Yes. What you do when you try to connect a solenoid with a current carrying battery or with a battery, what you observe, there is some field lines observed. There is some field lines observed, and it's the same thing. Or if the one line I will say that solenoid behaves as a bar magnet. Solenoid behaves as a bar magnet. Yes. If you can see magnetic field lines here, what I'm trying to say, suppose I am observing these field lines like this. The current is going like this inside this. It is moving like this. So if you observe from this side, suppose I am observing from this side. So what is the direction of current you are observing? Carefully see this coil. In this coil, the current starts going upward, then downward here. So from this observer which is standing here, the direction of current will be anti-clockwise. Yes or no? From the observer standing here, the direction of current in the coil will be anti-clockwise. And you know anti-clockwise means north pole. So here comes the north pole from the side where you observe. And the south pole is just behind this side. South pole is just behind this side, and you know the magnetic field line starts from north and terminates at south. So the basic thing you have to remember is how to perceive solenoid. From whichever direction you are observing, if the direction of current in the coil is anti-clockwise, then that side will behave as north pole. And if the direction of current is clockwise, according to us, then that side from which we are observing will behave as south pole. And the subsequent opposite side will be south or north pole. Yes, so you can see here magnet also, or solenoid also. Current is flowing. This is north, this is south pole. And the one important property about solenoid is that inside the solenoid, magnetic field is constant, because these are some kind of parallel straight lines you can see. This is a case of coil. Yeah, if you can observe one coil, these are a combination of different coils, from which around the coil or near to the coils, the magnetic field lines are circle. And when you go towards the center of these coils, the magnetic field lines are straight. So solenoid is nothing but a combination of different number of coils. And the effect of single coil we have already seen. Magnetic field lines circular near the coil. Towards the center, they are kind of a straight line. So the same thing is happening here. And the thing is that solenoid behaves as a bar magnet. That is, it is having a north pole and south pole, and magnetic field lines are this. One important property of solenoid is that inside the solenoid, magnetic field is constant. Inside the solenoid, magnetic field is constant due to the straight parallel lines. Straight parallel magnetic field lines. So magnetic field is constant, and magnetic field is highest at the poles for a solenoid. Magnetic fields is highest at the poles. That is the property of solenoid. These are the two important properties of a solenoid, that inside the solenoid, magnetic field is constant, or straight magnetic field lines, parallel magnetic field lines. Okay. And magnetic field is highest at the poles, that is south or north pole, or you can say ends of the solenoid, And the formula for magnetic field inside a solenoid is given by mu naught Ni by L. The formula for magnetic field inside a solenoid is given by mu naught Ni by L, where mu naught is known as magnetic permeability. This N is the number of turns, or you can say number of coils present in a solenoid. Yeah. I is the current flowing through the solenoid. And L is the length of the coil, or length of the solenoid. This is the formula for magnetic field in a solenoid, which is given by mu naught Ni by L. Clear? So I think solenoid is clear. It is basically a combination of various number of coils. Yeah. Inside the solenoid, magnetic field is constant. Near the edges or to the south or north pole of a solenoid, magnetic field is strong. Done? Yes, thumbs up, guys. Okay. Now see some questions. What we are seeing, choose the incorrect statement from the following regarding magnetic field lines. So we have to choose the incorrect statement. So we have to see all these statements first. So first statement is that the direction of magnetic field line at a point is taken to be the direction in which the north pole of a magnetic compass needle points. So this is correct basically. That whenever you are observing the magnetic field direction, so if you point a magnetic north pole, or if you point a compass needle here, and the north pole is like this, So this will be the direction of magnetic field, because there is a property in needle that the compass, or I can say compass is a property that the north pole of the compass will be aligned in the direction of the magnetic field of Earth. Will be aligned in the direction of magnetic field of Earth. Yes. So this is the property that whenever you align a compass, then the direction of magnetic field will be aligned like this. Second point, magnetic field lines are closed curves. Yes, magnetic field lines form closed curves. So this is also correct. See, if magnetic field lines are parallel and equidistant, they represent zero field distance. This is wrong, because I have already told you in solenoid, if magnetic field lines are parallel and equidistant like this, so it will represent a uniform magnetic field. Uniform or constant magnetic field, not zero. It will form a uniform magnetic field, not a zero magnetic field. So the thing is clear, this point is wrong. The relative strength of magnetic field is shown by the degree of closeness of field lines. Yes, very true. More the number of field lines or closer the number of field lines, stronger will be the magnetic field strength. So this is also correct. So the question was asking incorrect statement. So the only incorrect statement is option C. So our answer will be C. Yes, clear? Done. Okay, now next. If the key in the arrangement figure given below is taken out, what he's doing is taking the key out. So if you take the key out, the circuit will be open. Circuit will be open. And you know in open circuit, current is zero. There is no current flowing in an open circuit. Yes or no? So the current is not flowing in this question, in this arrangement. So if the key in the arrangement figure given below is taken out, that is the circuit is made open, and magnetic field lines are drawn over the horizontal plane ABCD. If you draw the magnetic field lines over here, then the lines are. First of all, if no current is flowing, there will be no magnetic field according to Oersted. According to Oersted experiment, if there is no current flowing in the case of open circuit, there will be no magnetic field. So the only magnetic field on the compass needle will be due to the magnetic field of Earth. Because magnetic field of Earth is always present. So only field acting on the compass needle will be magnetic field of Earth, and magnetic field of Earth is kind of straight line. Magnetic field of Earth are a straight line parallel to Earth's magnetic field. Why straight line? Because Earth has a very big radius. Earth is acting like a very big bar magnet. So if you observe the field lines, it will be like this, forming closed curves, but along the Earth. So if you see, we are only a small portion on the Earth. So according to us, the field lines will appear as a straight line, because it is actually forming a very large radius closed curve, very, very, very large radius. So that's why the only field lines present here on the compass will be due to the Earth's magnetic field. So the answer will be C. We'll observe straight lines parallel to each other. That is due to the Earth's magnetic field. Clear? Because the current is zero. So according to Oersted, the magnetic field will be zero. Now see question 3. A constant current flows in a horizontal wire. So this is a horizontal wire in the plane of a paper from east to west. So the current is flowing like this. The direction of magnetic point at a point will be north to south. The direction of magnetic field at a point will be north. So he is giving you direction of magnetic field from north to south. You have to decide where should the point be lying so that the direction of magnetic field at that point will be north to south. So we will use the right hand thumb rule. We will use the right hand thumb rule. Suppose we are aligning in along the direction of current, because current is flowing from east to west. So the thumb will be like this, and the curl of the finger is like this. Curl of the finger is like this. So if you can observe, if this is the wire, this is east, this is west, then this will be north, this will be south. Yes or no? East, west, north, south. So what I am doing, I am aligning like this, and it is written in the direction of magnetic field, it's from north to south. This was north. North to south, north to south. So where is the direction coming? Just behind it or just below it. Yes. If you take a point just here below the wire, what will you observe? The direction of magnetic field on that wire will be north to south. This is north, this is south. It will be from north to south. So where should the point be lying? Below the wire. Where should the point be lying? Below the wire. If I again explain you, this is east, this is west. If it is saying it is acting on a horizontal plane, so this will be north, this will be south. East, west, north towards you, south towards me. East, west, north towards you, south towards me. So north to south represent like this. If I curl the fingers, this was the direction of thumb. If I curl my fingers, this is going towards south now. Sorry, north towards you. Now it is going north. And from north, it is going towards me south. So at which point it is going downward? Can I say the point is below the wire? If I am taking the point below the wire, what will be the direction of that magnetic field? It will be like this. The fingers will represent the direction. So it is coming towards me. So from north to south, it is coming when the point is directly below the 1. So this is actually how to decide the direction with the help of fingers. Fingers will show, or curl of the fingers will show you the direction of magnetic field at any point. Suppose I give you an example. Suppose this is a current flowing. Suppose this is point P, this is point Q. So if you can put your thumb along the direction of current, you will see at point P, my fingers are going inside the paper. So at point P, the magnetic field will be inside. And if you observe, if you make the complete curl of the finger, started from P, going downward and coming towards Q. So at Q, what will you observe? Q is towards the left of the wire. Na? This was right of the wire. So left of the wire, the current is, or the magnetic field is coming outside. So at point Q, the magnetic field will be outside. So this is how to decide the direction of magnetic field with the direction of fingers. Clear? So I hope everything is clear. We have studied Oersted experiment. We have seen whenever current flows through a conductor, it produces a magnetic field around it. Then we have seen magnetic field due to a straight current carrying conductor that will be concentric circles, and the direction of whose will be given by right hand thumb rule. Then we have seen magnetic field on a current carrying loop, that is at the near of the coils or near to the coil circumference, the field lines are concentric circles, and when you go towards the center, they will look like a straight arc. They will look like a straight arc. Then we have seen solenoid. Solenoid is basically a combination of number of coils. Inside the solenoid, the magnetic fields are constant because they are parallel. And near the edges, or you can say poles of the solenoid, the magnetic field is strong and the solenoid behaves as a bar magnet. And we have also seen what are magnetic field lines and properties of magnetic field lines that we have seen. So I think everything is clear. Yes. But still, in case of any doubt, you can refer to Ask IITians website. Yes. You can post your doubts there on the doubt forum. Doubt forum is present on the Ask IITians website. You can post your doubts there and get it resolved by the expert faculties. Okay. So we are done with this session. We have covered every topic. So thank you so much. Stay safe and enjoy. Bye.